An oil tanker ran aground today off the nation's northernmost ice-free port, Valdez, Alaska.
People are suffering. People are dying. Entire ecosystems are collapsing.
Exxon Valdez oil spill, climate change and catastrophe, changing planet, increased air temperature, investigating how will the increase in global temperature affect the ocean chemical ecosystem. The Exxon Valdez oil spill was the worst oil spill in United States history. 37,000 metric tons of crude oil spilled in Prince William Sound, Alaska. Essentially, this occurrence led to the death of thousands of organisms, significantly altering the ocean's ecosystem and causing immense economic despair. As climate change progresses, the NASA climate change projections provide a detailed view of future temperature and precipitation patterns around the world. The predicted temperature change for 2100 globally is 4.1 to 4.8 degrees Celsius. As the air temperature is increased due to climate change, the impacts of an oil spill are intensified. As the air temperature increases, the oil spreads over the surface of the ocean due to increased motion of oil molecules. This is represented by the picture below demonstrating low temperature versus high temperature movement of the molecules. Air temperature is increasingly getting warmer as time progresses, climate change posing a major threat to the future of our planet. With increased air temperature comes heightened effects of oil spills. As heat increases, molecules are more easily able to escape the surface, leading to the development of a heavy vapor above the spill. Vapors containing ammonia, carbon compounds, and hydrogen sulfide. Higher temperatures result in increased movements of molecules, or KMT. Oil has less IMF, but more movement and more evaporation. Oil evaporates more easily in warm temperatures. Water has more IMF, but the oil covers the surface layer of the ocean. While oil vaporizes, water will be blocked from experiencing similar phase changes. This interrupts the water cycle. As depicted on the diagram to the right, phase changes occur when the temperature is increased. While oil vaporizes, water is blocked from evaporating. Warm air picks up toxic pollutants from the oil and spreads them in the atmosphere. The long-term impact is of great significance. In terms of IMF, hydrogen bonding is strong, temperature impacting the molecular density of water less than oil. London dispersion forces are weak, therefore resulting in the spread of oil over time. As time progresses, the area of the oil spill will spread due to these weak forces, allowing for increased movement of oil over the surface of the ocean. Furthermore, the nitrogen supply in the ocean will increasingly become depleted. The oil molecules shown in red and the water molecules shown in blue show that the density of both water and oil decrease with temperature. However, since hydrogen bonding is strong, it will be less impacted. As we progress toward the year 2100, the oil spill will continue to spread due to increased air temperature. The effect of increased air temperature on the ocean's chemical ecosystem is immense. Increasing temperatures decrease the gases in the ocean, such as oxygen and nitrogen, thus having fewer essential compounds for life. This deeply impacts the ocean's corals, leading to coral bleaching in addition to other marine organisms. As temperatures rise, an increase in coral bleaching occurs. An increase in CO2 levels absorbed into the ocean from the atmosphere decreases calcification rates of coral reefs. Furthermore, rising temperatures cause corals to lose algae that live in the polyp tissues. Zooxanthellae is what gives coral its color. The corals and algae have a mutualistic relationship. The coral provides algae with a protected environment and compounds they need for photosynthesis. As it is expelled, as a result of warmer temperatures, coral loses its color. long-term impact of the oil spill in the context of increasing air temperatures is that oil blocks nitrogen from getting into the water. The solubility of gases in water decreases with increased temperatures. Nitrogen gas becomes less soluble and there is less nitrogen fixation. A solution cannot be formed as oil and water have different polarities. Therefore, the oil remains on the surface of the ocean, forming a barrier. Any remaining nitrogen in the water will be used by bacteria, which will ultimately deplete the water of its nitrogen source. While there are many different methods to clean the oil spill, to remove and collect the oil is the most effective. Not collecting the oil has the potential to cause long-term environmental impact. By collecting the oil, it removes it from the environment and it also protects the future of the planet. To simulate the spill, first I created the oil spill, and then I froze it and was able to remove the oil from the surface layer of the ice. As water is polar and oil molecules are not, oil cannot be dissolved in water, causing the oil to disperse on the surface of the ocean. Since its density is lower, it remains on the surface. Molecules with stronger IMF are pulled together tightly to form a solid at a higher temperature. Therefore, the freezing point is higher. Molecules with lower IMF will not solidify until the temperature is lowered further. Therefore, the oil will become a liquid at an increased rate compared to water, allowing oil to be collected from the surface of the solid ocean. In its application to the real world, this procedure would likely only need liquid nitrogen and the materials needed to collect the oil. The cost of liquid nitrogen required to clean the oil spill would be approximately $2,842,105.26.